Welcome to the 34th Theoretical-Physics-Colloquium. Today we have Professor Claudia Ratti from the University of Houston. She got her PhD in 2003 from the University of Torino in Italy. Afterwards, she had several two-year postdoctoral positions at the Technical University of Munich, ECT Stadt Trento, and SUNY at Stony Brook. After that, she had a postdoctoral position at the University of Wuppertal before getting a faculty position at the University of Torino in 2010. Since 2014, she was a faculty at the University of Houston, where she is right now. She received several honors and awards over the years. I should mention probably just a few of them. In 2019, she received Research Excellence Award at the University of Houston. In 2017, she received NSF Career Award. And in 2012, she had the Italian Academy of Science Prize Giuseppe Borgia for Best Italian Physicist below 35. That was awarded by the President of the Italian Republic with a good honorarium. She served as an elected member of RHIC Users Executive Committee between 2016 and 2019. Since 2018, she is a member of the editorial board of international journal Universe. Her expertise is in thermodynamics of QCD, from first principles, phenomenology of QGP, QCD equation of state, ADS-CFT correspondence, and many other things in strongly interacting matter. Today, she will be talking about QCD at finite density and phenomenology. So with that, microphone is yours.
Thanks a lot. Hello, everyone. It's a pleasure to be here. And I would like to start by thanking Igor for inviting me. And today I will be giving a presentation about QCD at non-zero density, mainly from the point of view of numerical simulations on the lattice, but also with some phenomenological inputs which allow us to explore some regions where the lattice cannot reach out yet. So let me start by a general introduction, and then I will get into the details later on. So basically, here is a schematics of all known elementary particles, and this talk will be focusing about the ones that feel the strong force, which are quarks and gluons. So, however, the strong force is very peculiar, and because as you try to pull quarks apart, they interact more strongly, so the strength of the interaction between them increases with the distance. And because of that, free quarks have never been observed, but they only come in bound states of either two, namely a quark and an antiquark, and those are called mesons, or three quarks, and those are called baryons. However, of course, if we want to study and understand the strong force, we would like to look at quarks directly. So physicists had an idea. So instead of trying to pull quarks apart and try to separate them and isolate a single quark, if we do the opposite, if we compress them and if we heat them, then maybe we can achieve a new state of matter where quarks and gluons are actually no longer bound inside protons and neutrons, but they are free to move over the whole size of the system. And this phase of matter is what we call a quark-gluon plasma. And that's the main topic that I will be covering today. So the idea is that as you increase the density of the system or the temperature, quarks and gluons are free. And when the temperature is very low, below the phase transition line, then they become confined inside hadrons. So in this animation here, the background basically represents the color of the background represents the temperature, if you want. So if you see that it is red, normally that associates with hot, and that's, as you see, quarks and gluons are free. And then let me play it one more time. When the temperature goes down towards the blue, then the quarks and gluons get confined and form these bound states of hadrons. So the idea is that we want to study this phase of matter, and there are several reasons for that, not only because we want to understand the strong force. In particular, here is a list of questions that the research councils of the national academies listed as 11 relevant science questions for the new century. And by studying the quark gluon plasma, we are able to answer 2 of them. How did the universe begin? And what are the new states of matter at exceedingly high density and temperature? In fact, the quark gluon plasma is the state of matter that you can achieve at exceedingly high density and temperature, because in order to get there, in order to create it, you need a temperature which is more than 100,000 times the temperature in the core of the sun, and densities that you would achieve by squeezing the whole Earth into the size of a basketball. And besides, this phase of matter, we believe, was the one that populated the whole universe at the beginning of its evolution, just a few microseconds after the Big Bang. So imagine the whole universe was just a hot soup of quarks and gluons. So what are the questions that we are trying to answer? What are the goals that we want to achieve? So here I have something that you know very well, which is what we call a phase diagram for water. And so the idea is that if I tell you a value of the pressure or a value of the temperature, I hit a point on this phase diagram, and we know it so well that you can immediately tell me whether at these values of pressure and temperature, water is in a solid state or in a liquid state or in a vapor gas state. So we would like to achieve the same level of detail of understanding the phase diagram of strongly interacting matter. So in this case, things are not so simple. And as I will show you in the rest of my talk, we don't know, still a lot of regions or areas of this phase diagram are not well known. What we do know is that for low temperature and density, as I discussed so far, quarks and gluons are confined inside protons and neutrons. And then either when we increase the temperature or the density of the system or both, we can reach this new phase of matter, which is the so-called quark gluon plasma. So here I have another pictorial representation of the phase diagram, which I like very much because not only it shows this phase transition line, but it also shows a lot of experimental facilities that try to investigate this phase of matter, and they cover different regions of this phase diagram. So here I also have on the left a list of questions that we are trying to answer when we study this phase of matter. And in particular, one of the main open questions in our field that right now is the focus of some experimental program that I will discuss in a little while is whether there is a critical point on this phase diagram which separates a crossover transition, which we know for sure is the phase transition order at small densities and high temperature, from a first order phase transition, which is postulated to exist at high densities and lower temperature. So the search for this critical point is something which is right now the focus of some experimental programs that I will discuss. So the key to answer these questions is really a systematic synergy and combination of efforts between theory and experiment. So this question, this system is so complex that we need to join forces between different methods to really understand all of the aspects of it. So from the theoretical point of view, the tool that we have to study the quark gluon plasma is the fundamental theory of strong interaction, which is called quantum chromodynamics. And it describes basically the interaction among quarks and gluons. And here in this figure, you see a little bit more quantitatively what I had already anticipated, which is the fact that the strength of the interaction increases when you try to pull quarks apart. So you see that this is what we call the coupling between quarks and gluons, and this coupling is not constant, but it can be large in the area region which we call confinement, and it becomes small and lead to the liberation of quarks and gluons and asymptotic freedom. And then we have, on the other side of this slide, the experiments. So experiments that can currently create the quark gluon plasma in the lab are called heavy ion collisions. And basically the idea is that you can collide two heavy nuclei and create at ultra-relativistic energies and create this phase of matter in the lab. And indeed, this was created, and it is routinely created at RHIC in two labs on Earth, at the Relativistic Heavy Ion Collider on Long Island and the Large Hadron Collider at CERN. And what was found was that this quark gluon plasma is actually not a plasma, but it behaves like a liquid, not only a liquid, but the most perfect fluid ever observed, which means that it has a very low viscosity. And if you think about it, this was unexpected, and it was something that was discovered experimentally. And if you think about the consequences of that, this means, for example, that the early universe was entirely in a liquid phase just a few microseconds after the Big Bang. So before I move on to the theory, which is really the focus of my talk because I'm a theorist, I just would like to spend a few words about what happens in a heavy ion collision in the lab. So here is the Relativistic Heavy Ion Collider at Brookhaven Lab. And what happens there is that you accelerate gold nuclei, which have 197 protons and neutrons each, and then they are injected into this main ring where they, which has a circumference of about 3.8 kilometers. And there they go extremely fast. So they go through the experimental apparatus and they collide with each other about 100,000 times per second. So it's a huge amount of statistics and a huge amount of data that is collected in these experiments, and that then can tell us something about the properties of this new phase of matter. And the RHIC machine is extremely interesting for the topic of my talk, which is QCD at finite density, because you can systematically decrease the collision energy. And by doing that, you increase the baryonic chemical potential, or the density, which is this axis on the phase diagram. So by decreasing the energy, you can systematically reach into the higher density phase on the phase diagram. And this basically is done in small steps of decreasing the collision energy. And here you see all of the values that are going to be explored. And the idea is that basically by doing so, you hope to scan in a beams of energy which are, they have a small enough step to hit somehow the critical point. So these are the values which are going to be explored in terms of collision energies in the collider and fixed target mode. And here you see the corresponding values of the chemical potential that will be achieved. And on top of that, the study of high density matter will not finish with RHIC, but there are experimental facilities which are either about to start taking data or being built right now, which will study either the critical point or the onset of the confinement or dense hadronic matter, at least until 2025, but also way late, probably later than that. Okay, so this is basically all I wanted to tell you about the experimental side of things, but as we will see later on in my talk, I will also present comparison with data, so somehow the experiments will still come back. But now I would like to focus on the theory of strong interactions, which is quantum chromodynamics, and the people who invented this theory got the Nobel Prize in 2004. And like I said, it is a very peculiar theory because the interaction between quarks increases with the distance between them. And because of that, analytical solutions of QCD are not possible in the non-perturbative regime mainly when the coupling is large. And that is the regime which is interesting for the experiment, because that's the regime in the vicinity of the phase transition that we want to study. So the only way that we have to solve the theory in that region, which is interesting, where quarks get liberated, is by solving QCD numerically on a discretized space-time grid, which we call lattice. And these simulations are extremely expensive from the computational point of view, and they run on some of the most powerful supercomputers in the world. So because it's a numerical method, of course, Lattice QCD will be hindered both by statistical and systematic errors. But if you have enough computer power and if you optimize your algorithms, at the end of the day, you get some results where you can really shrink the error bar and get some very reliable predictions that you can go and use either in direct comparison with experiments or as inputs of other models that then can describe the evolution of the heavy ion collision. So how can we support the experimental program with Lattice QCD? And that is basically the main topic of my talk. And we can provide observables that that are relevant for the experimental program. And here I list the ones that I will focus on, because these are also the ones which are my main topic of research, and they are the ones which right now are precise enough that a direct comparison with experiments is possible. So these basically are the equation of state, which is not directly comparable with the experiment, but it is needed as an input for hydrodynamic simulations that can be run and describe the evolution of the system created in the heavy ion collisions. Then I will talk about what we know from first principles about the QCD phase diagram itself, in particular where the transition line lies on this temperature and density plane, and which constraints we currently have from first principles about the location of the critical point. And finally, I will talk about some observables, which are called fluctuations of conserved charges, which are extremely interesting because they can be simulated on the lattice and measured in experiments. And if we take some experimental features into account and correct our data for those, we can directly compare Lattice QCD results to the experimental measurements. And they are also sensitive to the critical points, so they are also very important because they are a good signature. If a critical point exists, they diverge, and therefore, if we look at them, we can, if we see some behavior which is related to a divergence, we can spot the critical point. So as we will see, these fluctuations are extremely important for mapping out the phase diagram of QCD. So let me start with the QCD equation of state at finite density. So I will touch on the methods that are used to extract it, and then present to you the results that we have currently on the lattice. And here, towards the end of this topic, I will also mention a more phenomenological approach that allows us to study the effect of the critical point on the equation of state. So let me start with actually the baseline, which is the QCD equation of state at 0 chemical potential, so at 0 density. That's already known in the continuum limit since 2013. And we have two different collaborations, the Wuppertal Budapest, of which I am a member, and the Hot QCD collaboration, which independently found results for this equation of state. Here you see, for example, the pressure in green, the entropy density in blue, and what we call the interaction measure in red, as functions of the temperature. And the gray points are results from the hot QCD collaboration, whereas the colorful ones are from Wuppertal Budapest. And you see that the two collaboration results agree with each other within error bar, which is a very important validation of the theory, because it's important to test that the two simulation setups, which are very different from each other, in the end give the same results in the continuum limit. And here on the right-hand side, you see also some newer results from Wuppertal Budapest collaboration, where we also included the effect of the charm quark. So the red results are the equation of state, which I showed here on the left, which are basically a system in which you have up, down, and strange quarks. And then the black results are a system in which you also include the charm quark. And you see that in that case, the equation of state starts to deviate from the 2+1 flavor case at temperatures which are of the order of 250 MeV. So for the LHC, for example, where the temperatures which are achieved are very large, of the order of 500 MeV, including the charm quark, it turns out to be important, and you cannot just neglect. So an important validation on the equation of state of QCD came actually from this Bayesian analysis that I show here, where basically a large number of experimental data from RHIC have been systematically studied and compared to theoretical models while changing the model parameters in a systematic way. And one of the inputs in the models was the equation of state. And it turns out that the posterior distribution that you get from this Bayesian analysis agrees with the Lattice QCD equation of state that I showed you before. So this was a very nice result, because it shows that basically the system that you are looking at in a heavy ion collision follows an equation of state, which is the one which is simulated in Lattice QCD. So moving on to the finite density part, it's important to say that we are immediately limited in what we can do on the lattice, because of a very well-known numerical problem, which is called sign problem. So this is a problem which affects theories at finite density, and basically it affects the intrinsic method that we use to simulate, to solve the theory numerically, which is Monte Carlo techniques. So these Monte Carlo simulations are not applicable in the case of a finite chemical potential. And because of that, that's the main reason why the equation of state is not known over the whole QCD phase diagram, and the phase diagram itself is not known for all values of the temperature and densities. So we basically, what we can do right now is to try to circumvent the sign problem by applying some techniques which allow us to at least explore some limited region of chemical potential, which is not too large. And these techniques in particular that I will be focusing today on are either the Taylor expansion method or a numerical simulation at imaginary chemical potential, which are possible because there is no sign problem, and they are analytical continuation of these results to real values of the chemical potential. So for example, in the case of the Taylor expansion, you see here that you can write the pressure of QCD at finite temperature and baryonic chemical potential as a Taylor series in powers of mu b over t. And basically you have the zeroth order term, which is basically the pressure at mu b equals 0 that I showed you 2 slides ago, which we have. And then going on, if you want to go to finite mu b over t, you get these expansion coefficients that are simulated on the lattice still at mu b equals 0. So you can still simulate them. And then you can plug them into your expression here and treat mu b over t as a parameter that you can change numerically. It's just a dimensionless quantity, so you can choose a value 0.5, 1, and so on, and see how your equation of state looks like. So the key in this kind of expression is to extract these coefficients from lattice QCD. So as soon as you go to finite chemical potential for the baryon number, you also want to make a choice on the other two conserved charges of QCD, which are strangeness and electric charge. So the two typical choices which are made are either to set mu b finite, so different from 0, but to keep still mu s and mu q equal to 0. Or the more popular choice, because that's relevant for phenomenological applications, is to choose mu s and mu q as functions of temperature and baryonic chemical potential, which satisfy these conditions. So these two conditions are two phenomenologically driven conditions, which tell us that the net number density of strange particles is 0, and the net number density of electrically charged particle is equal to 0.4 times the net number density of baryons. So where do these two conditions come from? They basically come from the initial conditions in a heavy ion collision, because you are colliding two nuclei which don't contain any strange quark, because protons and neutrons inside the nuclei only contain up and down quark. So the net strangeness at the beginning of your collision is 0. And because strangeness is a conserved charge in QCD, you expect to have an overall zero strangeness also when you evolve your system. And this is this first condition here. And the second one also comes from the initial condition that the nuclei that we collide have a slightly lower number of protons compared to neutrons. So the proton plus neutron gives you the total number of baryons in the initial collision, in the initial conditions. And then this NQ is basically the fraction of proton over baryon that you have in the two nuclei that you collide. So this 0.4 is more or less a number which is valid both for gold and for lead, which are the nuclei that we consider. So if you want to have an equation of state that basically matches this condition, which are experimentally relevant, then you can fix the strangeness and electric charge chemical potential such that they obey these two conditions. And then you have an expansion as a Taylor series in powers of mu b over t in a direction which is not the mu b equals 0 axis, but is a direction in the four-dimensional phase diagram of T, mu b, mu s, and mu q, which satisfies this condition. So we have results for the Taylor expansion coefficients for both cases. So here at the top, you see results from the Wuppertal-Budapest collaboration in the case of strangeness neutrality. And in this case, here we have the second order Taylor expansion coefficient for the pressure, the fourth order, and the sixth order. And here at the bottom, you see new results for the case in which mu s and mu q are both equal 0. And in this case, we don't have a continuum extrapolation yet, which we have up here, but results at finite lattice spacing so far. And here, however, we were able to go one order higher in the Taylor series, and we have fourth order, sixth order, and eighth order coefficient. So with these results, which portion of the phase diagram are we able to cover with our equation of state? So here you see it. So we have results that we are confident allow us to expand our Taylor, our thermodynamics as a Taylor series, covering this triangular shape of the phase diagram, which corresponds to mu b over t smaller or equal to 2. And this corresponds in terms of beam energies more or less to these values. So as you can see, we are not able yet to cover the whole beam energy scan 2 range, which goes in the collider mode down to 7.7 GeV. So we need to go higher order in the Taylor expansion to be able to bend this triangle to larger values of mu b over T. So now, before I continue with lattice results, I would like to briefly discuss an equation of state which we constructed within the BESII collaboration, which basically builds on what we learned from Lattice QCD and which I discussed so far, but also allows us to include in our system a critical point which we can put in by hand and which is in the correct universality class for QCD, which is the 3D Ising model. So the idea is that critical points in nature only come in a certain set of universality classes, and the one of QCD happens to be in the 3D Ising model universality class. And that's basically very convenient because the beauty of universality is that if you know how a theory like the 3D Ising model behaves in the vicinity of the critical point, then all other theories which share the same universality class will behave in the same way in the vicinity of the critical point. So what we did was to construct an equation of state which basically matches lattice QCD for the Taylor expansion coefficients up to fourth order that that I showed you that we can obtain from the lattice. But then it also contains a critical point, and the matching is done by assuming that the lattice coefficients are made out of a contribution from the Ising model that is known in the literature and we can calculate, and then a non-Ising contribution, which is basically the difference between the lattice and the Ising contribution. And once we do that, we can expand then reconstruct the full pressure, and from there extract all other thermodynamic quantities. So here, for example, I show the entropy density and the baryon density, which both show a discontinuity for values of the chemical potentials larger than the critical point where you have a first order phase transition. So the beauty of this approach is that basically you can download this code from this web page, and then the users can change the location and the strength of the critical point at will. And the idea is that when the data from the second binary scan become available, one can feed this equation of state into hydrodynamic simulations, and by systematically changing the values of the location and strength of the critical point, one can compare two experiments and hopefully gain some constraint on the location of the critical point. Okay, so this is what I wanted to tell you about the equation of state. Now I'm going to move on and talk about what we know from first principles about the actual phase diagram of QCD. So it turns out that the transition of QCD at mu b equals 0 is a smooth crossover, as I already anticipated, and this is known since 2006. And what this means is that if you look at observables like this one here, which is what we call chiral condensate, which give you an idea of the phase transition, they can be called order parameters because they behave very differently in a hadronic phase, like up here at low temperature, where this quantity is basically tending to 1, and at very high temperature, where you are in the quark phase, where this quantity tends to 0. So this is what we call a pseudo order parameter because you don't have a real phase transition, and that's why this quantity behaves very smoothly as a function of the temperature. However, you still can see that for low temperature or high temperature, it tends to two very distinct values. And then you see that in between, there is a rapid decrease of this quantity. And by looking, for example, at the derivative of this quantity with respect to temperature, you can observe a peak, which will basically be used to identify the value of the transition temperature. So the idea is that we look at these at quantities like the chiral condensate and its derivative, which is called chiral susceptibilities. And by studying them either at imaginary chemical potential or by Taylor expanding them to finite mu b, we can study how the location of this peak in the chiral susceptibility changes with the chemical potential, and that gives us a transition line, which is the transition temperature as a function of mu b. So the transition line itself can be written as a Taylor series in powers of mu b over t. And here you see that we have the value at mu b equals 0 is the transition temperature at mu b equals 0 itself. And then you have other coefficients which basically parameterize this line on the phase diagram. And right now we have values for kappa 2, which is the curvature of the phase diagram, and for kappa 4, which is the fourth order, the parameter in front of the fourth order term. So the most recent results from my collaborations were published this year in PRL. Here is the reference for them. And basically, we have the most precise results for the value of the transition temperature at mu b equals 0, based on chiral observables, which is about 158 MeV. And then we have, here is a compilation in the literature of values of kappa 2, the curvature of the phase diagram, and down here we have our new results. And then we have there are in the literature two results for kappa 4, the previous one by the hot QCD collaboration, and our new results where you see that the error bar was considerably shrinked. And you can see that kappa 4 is basically consistent with 0 within error bar. So the phase diagram starting off and reaching out at finite chemical potential from the temperature axis behaves like a parabola effectively with this curvature, which is also very small. So you have a very flat line leaving the temperature axis. Another very interesting quantity that we have been focusing on is the width and the height of the peak of the chiral susceptibility. These two quantities are very important because if you have a first order phase transition, the chiral susceptibility at the critical point diverges, and therefore this means that the height of the peak goes to infinity and the width of the peak basically shrinks to 0. So what we did was to study the behavior of the height of the chiral susceptibility peak and the width of the peak going from the 0 chemical potential down to larger values of the chemical potential. And of course, we don't expect to reach a critical point at 300 MeV, but maybe if you are approaching the region where the critical point effects can be felt, you would expect to see an increase in the height of the chiral susceptibility peak and a decrease in the width. But as you can see in the explored range of chemical potentials that we looked at, here you see the value expressed in terms of mu b over t squared, but here it's in the case of the width of the peak, you can see it in MeV, and you see that both quantities basically are flat and consistent with the constant. So we don't see any sign of criticality from the lattice point of view for chemical potentials smaller than 300 MeV. However, what I would like to point out, which is also very interesting, is that the value of the width of the chiral susceptibility peak itself can be taken as an indication of the width of the crossover transition. So you see that this crossover, this is the half width. So you can think about the crossover as being centered around this value of temperature that I showed you here, 158 MeV, but then having a width of plus minus about 14 MeV. So it's a quite broad transition line, which is pretty clear also from the fact that if you look at the observables, they change very smoothly over a range of temperature, which is indeed of the order of 20 to 30 MeV. Okay, so now I would like to come to my last part of the talk, where I focus on these fluctuations of conserved charges, which are the observables which we can compare to experiment, provided that we take into account all non-thermal fluctuation sources. So why are these observables relevant? So before I talk about them specifically, I would like to discuss for a minute the evolution of a heavy ion collision. So here you have a cartoon where you see what happens in a heavy ion collision in a little bit more detail. So we already talked about the fact that you collide two nuclei, for example here lead nuclei, and when they collide, they form this colored area here, which corresponds to the quark-gluon plasma. And then as the time goes by, your system is expanding and the temperature is decreasing. And therefore, at some point from this deconfined phase of matter, you hit the phase transition line, and there your system hadronizes and forms bound states of quarks and gluons called hadrons, as we have seen. So then these hadrons will continue to move, and finally they will reach the detector. And in this hadronic phase, there are two important points that we can clearly identify. The first one is called chemical freeze out, and that's the time in the evolution of the system where all inelastic collision between hadrons stop. So this means that you cannot have reactions anymore which change the nature of your particles. So the chemical compositions of the system is fixed at this point. So if you have a net number of charges at this point, that gets fixed there. It doesn't change anymore until it hits the detector. So basically everything which has to do with the hadrochemistry of your system is fixed at the chemical freeze out. And that's the point in the evolution of the system that I will focus on from now on, because fluctuations of conserved charges are fixed at this chemical freeze out as well. So the value that we measure in the detector reflects the value that was that these quantities had right here at this point. And then as the system keeps expanding and cooling down, there is a second point which is relevant, which is called thermal freeze out, where also all elastic reactions cease, and that's where the spectra get frozen, and from there on you just have free streaming to the detector. So why do we care about the chemical freeze out so much? Well, we would like to understand how far the chemical freeze out happens with respect to the phase transition line. So you see here that in this cartoon, we have the quark-gluon plasma turning into hadrons at this point. So this colorful area is the QGP, and then it becomes hadrons here, which is color neutral. And then these hadrons hit the chemical freeze out a little bit later. So what does it mean in terms of phase diagram? Here we have the phase transition line. Where does the chemical freeze out line sit compared to the phase transition line? That's important. That's an important question, because imagine that you are looking for the critical point. The critical point sits on the phase transition line, but its effect probably is not limited to just one point on the phase diagram, but there is what we call a critical region around the critical point, where the effects of the critical point are still visible. So if your chemical freeze out is very close to the transition line, then you have a good chance to observe some critical point effect also at the chemical freeze out, even if you are not sitting on the critical point itself. But if the chemical freeze out should be very far from the phase transition line, then you risk not to see the effect of the critical point because you are too far to feel it. So that's why we are interested in where the chemical freeze out happens compared to the transition line. So what are the experimental data that we are looking at, that we are calling fluctuations, and what do we measure And in the end, what do we calculate on the lattice to compare to the experiment? So let me start with the experimental measurements. So what we do, imagine you have a heavy ion collision, and at the end in your detector, you count the net number of, for example, electrically charged particles, so positive minus negative. And for one collision, you get a certain number, let's say, for example, 50. Then you repeat the collision, you get a different number of electrically charged particles that hit your detector, let's say 20. So at the end of the day, when you repeat your procedure millions of times, you get a distribution which looks like this, where you have an histogram which tells you the number of events in which a certain number of net electric charge particles were hitting the detector. So here you see this distribution obtained by the star collaboration for different values of the centrality and different values of the collision energy, starting from 200 GeV, where you see that the peak sits more or less at 0. And then as you move towards lower energies, this means higher densities, and you see that the peak of this distribution moves towards positive value. So at the end of the day, once you have your distribution, you can also go and calculate quantities which typically characterize a distribution statistically. For example, the mean that we already discussed, so the location of the peak, and then the variance, which tells you how broad your distribution is, the skewness, which tells you whether it is symmetrical or asymmetrical, and the kurtosis, which basically tells you how peaked your distribution is. So these numbers, quantities, mean, variance, skewness, and kurtosis, are called cumulants of the distribution. And they basically are quantities that we can measure, that the experimentalists can provide. And the nice thing about it is that they can be related one-to-one to something that we can calculate in theory, which are these fluctuations of conserved charges. So the idea is that the fluctuations from the lattice point of view are nothing else than derivatives of the pressure with respect to the chemical potential of the conserved charge that you are interested in. For example, if you want to study the distribution of electric charge from the experimental point of view, then your fluctuations are related to the cumulants, and these fluctuations are just derivatives of the pressure with respect to the electric charge chemical potential. So here you see the most general expression for them, where we have diagonal or non-diagonal derivatives with respect to all three conserved charges. And the focus at the beginning will be just on the diagonal ones. Those I will discuss first, but then I will also briefly touch on some new results when you start looking at correlations between different conserved charges. So the idea is that the variance of the distribution, which the experimentalists measure, is on the lattice the second order derivative of the pressure with respect to the corresponding chemical potential. The skewness is related to the third and second order derivatives, and the kurtosis is the ratio of fourth order to second order derivative squared. So typically these quantities depend on three variables: the temperature, the chemical potential, and the volume. And the volume dependence, the leading order dependence, is just a linear multiplicative factor in front of these quantities that you can get rid of by taking ratios, so that these ratios to leading order on the lattice only depend on two variables, which are the temperature and the chemical potential. And from the experimental point of view, for each collision energy, you get one number that you can compare to your lattice QCD surfaces in the TMUB plane. So the idea is that if you fit two of these quantities, you can fix for each collision energy the temperature and the chemical potential of the chemical freeze-out. Of course, when we want to do this comparison, we want to make sure that the fluctuations that you measure in experiments are actually thermal fluctuations that you calculate on the lattice. So there are some effects which can affect the experimental results, which need to be taken into account and corrected for in order to make a meaningful comparison. So here we see our results for these observables, and we have performed a combined fit of two of them in order to have the temperature and chemical potential of the chemical freeze out for different collision energies. And in particular, we looked at the mean over variance of electric charge and baryon number and performed a combined fit of those. And here you see the results, and this is a very dense plot that I would like to spend a couple of minutes on to explain it well, because it's one of the main results from comparing Lattice QCD to experiment. So these colorful trajectories on the T and mu B plane that you see here are the values of T and mu B, which satisfy the experimental value for chi1 over chi2 for electric charge for the solid line and baryon number for the dashed line. So the point where they meet is the combined fit result, which gives you this point here, which is the chemical freeze out point. And you see that you have several collision energies, 200 GeV, 62.4, 39, 27, and 19. And those basically give you, for each collision energy, you can repeat the exercise and get these freeze out points. So now you see also something else on this graph, which is this band, which basically corresponds to the crossover that I discussed before, which was also obtained from Lattice QCD simulation. So this is the width of the crossover, which is very broad, and the chemical freeze out points that we obtain sit towards the bottom of this crossover transition line. And also you see these trajectories here. For each collision energy, you can take the value of T and mu B that the system had at the freeze out, calculate there the entropy per baryon on the lattice, which will give you a certain number. For example, here it's 420, here 144, and so on. And then impose that as you change the temperature and chemical potential, this value is conserved. And basically, this gives you these trajectories in the phase diagram, which are approximate trajectories that your system would follow if the viscosity of the quark-gluon plasma was strictly zero. So we know that the viscosity is non-zero, but it is relatively small. So these are from Lattice QCD calculations, indications of the trajectory in the T and mu B plane that your system followed in a heavy ion collision. So you can imagine that when you collide the two nuclei at 200 GeV, your initial temperature is somewhere up here, and then as the system expands and cools down, it follows this trajectory in the phase diagram until it hadronizes, and then it hits the chemical freeze out. So this is basically a summary of the things that we can do nowadays from Lattice QCD point of view to compare with experiments. So one point that I would like to make is that the baryon number and the electric charge are dominated by light flavor. So one could ask, what about strangeness? So I don't want to spend too much time on that. I just want to give you a hint that we did look at strangeness, but not directly from the lattice point of view, because we had only from the experimental data only net kaon fluctuations, which we can take as a proxy for strangeness, but you cannot directly compare to strangeness fluctuations on the lattice. So we did an analysis of net kaon fluctuation in a phenomenological model called the Hadron resonance gas model. And if you fit those, you will see that they need a higher temperature to freeze out compared to the light flavor. And a separate analysis on some other quantities that I didn't have the time to discuss, which are particle yields, gives also a similar results. And for example, here you see a plot, which is from this publication from the Houston group, where they looked at the light versus strange chemical freeze-out points. And you see that the light ones are consistent with the ones that we found, and they sit indeed towards the bottom of this phase transition crossover region, and the strange temperature, the strange freeze-out temperature, sit towards the upper end of this broad crossover region. So just briefly, I would like to say that the STAR collaboration has started to look into off-diagonal correlators of conserved charges, and in particular, they looked at correlations between protons and kaons, charge and kaons, and charge and protons, to see whether they can be considered as good proxies for baryon strangeness correlators, charge strangeness correlators, and charge and proton and charge and baryon number correlators. So as you know, in Lattice QCD, we cannot distinguish the contribution of a single particle, but we work in terms of global conserved charges like baryon number, electric charge, and strangeness in the grand canonical ensemble. So which quantity that I can measure in experiment relates one-to-one to a baryon strangeness correlator that I can calculate on the lattice? That was the question that we were trying to answer, and we wanted to check whether these initial data from STAR are indeed good proxies for the correlators of conserved charges that one can calculate on the lattice. So we looked at, we did this analysis by comparing the lattice results to the Hadron resonance gas model results. And in particular, the problem is that experimentally you cannot measure all particles that you would need to reconstruct a full conserved charge. In particular, here are the quantities, the particles that typically are measured in experiment. And inevitably, you lose a good chunk of conserved charges by only measuring these quantities. In particular, for example, by not measuring neutrons, you are missing a good chunk of baryon number, and so on. So we looked at the contribution to the baryon and charge, baryon strangeness and charge correlator coming from these measurable particles, which is the blue line, and the non-measurable ones, which are neglected in experiment, they cannot be measured, which is the red line. So you see that in the case of the baryon charge and charge and strangeness correlators, the measurable particles give you basically almost all the contribution, whereas in the case of baryon strangeness correlators, the contribution is almost equally split between measurable and non-measurable particles. So we looked in more detail at the baryon strangeness correlator, and we figured out that if you look at the ratio between baryon strangeness correlator and just the second order strangeness fluctuation, then you can find a good proxy based on just measurable quantities, which gives you basically the full result. So this is the total curve from the Hadron resonance gas model point of view. And you see that, for example, if you consider the variance of the lambda particles divided by the variance of the lambda plus kaons, which are quantities that you can measure in experiment, and this would be this blue line here, this gives you a good proxy for the total baryon number and strangeness correlator divided by second order fluctuation of strangeness that you can measure on the lattice. So we did a preliminary analysis of data from STAR for this lambda sigma square of the lambdas divided by sigma square of lambda plus kaon compared to our proxy. And you see that if you take the proxy at the value of the temperature, which is 165 MeV, which is compatible with the strangeness freeze-out temperature that I showed you before, then indeed you can reproduce the results. Whereas if you take a freeze-out temperature of the order of 145 MeV, which is the light flavor freeze-out, you cannot reproduce this data. So indeed, this quantity, which is again related to strangeness, seems to prefer a higher freeze-out temperature compared to the light particles. So I'm running out of time, and I just have a very quick result that I would like to discuss, which is a little bit more phenomenological, but it is very exciting because it is a prediction that we made about the location of the critical point. So we made this prediction based on fluctuations of conserved charges because they are expected to diverge at the critical point as powers of the correlation length, and in particular the fourth order fluctuation diverges with a large power of the correlation length, and therefore if you look at them you can identify the divergence in the fluctuation and relate that to the location of the critical point. So which approach did we use to do this analysis? We used, of course, not Lattice QCD because you cannot push it currently to very large densities, but we used a holographic approach, which is basically able to reproduce every single thing that I showed you so far from the lattice. And on top of that, it also reproduces the feature of the quark gluon plasma being an ideal fluid. So the ideal fluidity of the quark gluon plasma, which is something which is related to its transport properties, and everything that we know from the thermodynamic point of view is reproduced by this approach. So we believe that because that's the only approach known in the literature which can reproduce both features, the thermodynamics and the transport properties, we believe that this is one of the most realistic approaches to use to make a prediction on the location of the critical point. So what we did is we looked indeed in this approach. I will not spend too much time on describing it, the approach itself, but rather focus on the results. We looked at fluctuations chi2, chi4, chi6, and chi8. As you see, at mu b equals 0, where we have lattice QCD results for these quantities, the predictions of the model are able to reproduce the lattice QCD results. But then we can also look at how these fluctuations evolve at high values of the chemical potential. And you see that both chi2 and chi4 develop a pronounced peak as you increase the chemical potential. So if you follow the behavior of chi2, for example, as a function of T mu b, at some point it will diverge. And that location of that divergence we identified as the critical point. And this critical point turns out to be located at 723 MeV chemical potential and 89 MeV temperature. So if you think about the phase diagram that I showed you, it sits very much in the high density, low temperature region. And however, we made a prediction that in order to heat it, you need a collision energy, which is between 2.4 and about 4 GeV. So RHIC in the fixed target mode should be able, if the critical point is indeed there, to see it. So we are very much looking forward to the RHIC results to see whether our prediction for the location of the critical point gets indeed confirmed. So this finishes my talk. Let me come to my conclusions. So like I told you, we need quantitative results from the theory at finite density to support the experimental programs which are currently running. In particular, the focus of this talk was about the RHIC beam energy scan program that scans the phase diagram in the search for the critical point. Lattice QCD is able to provide information about the equation of state, phase transition line, and fluctuations of conserved charges. But at the moment, we are still limited to values of the chemical potential over temperature, smaller or equal to 2. So I also showed you some other approaches which are more phenomenological that allowed us to explore higher densities. For example, the 3D Ising model equation of state with the critical point, or this holographic approach, which allowed us to predict the location of the critical point in the phase diagram. From the lattice point of view, strictly speaking, however, we didn't see any indication of the critical point for chemical potential smaller than 300 MeV. So this tells us that if indeed the critical point should be located where we predicted it from the holographic point of view, that's not surprising that we don't see any effect of it at small values of the chemical potential that we were able to cover with the Lattice QCD simulations. So this concludes my talk. Thanks a lot for your attention.
Well, thank you very much for a very nice presentation. Now we will have some time for questions. So let's start with the questions. I see Michael Strickland is raising a hand. Go ahead.
Hi, Claudia. I was wondering
Hi.
if there's any effort to try to look at also the curvature of the phase transition line in the isospin direction. So as a function of mu I.
Yeah, so that's
would be important, I guess, for some people who are modeling neutron star mergers and stuff to have some.
Yes, that's a very good question. And I think there are some results from the hot QCD collaboration that at least have looked at the curvature in the direction of the other two conserved charges, which are electric charge and strangeness. So I'm not sure if they quote exactly the isospin, but for sure there is, you can extract the isospin chemical potential as a linear combination of the baryon number and electric charge, so you and strangeness, so you can probably reconstruct it from there. And there are also results from Gergely and Rodi, where he has actually mapped out not only the curvature of the transition line, but the whole phase diagram in the T and mu isospin chemical potential plane. So you can actually look, if you, I can give you the reference in his page, but if you look under Androdi, you will find it. You can find actually the whole phase diagram mapped out there.
Thanks.
Okay. Any other questions from the audience? I don't see immediately anybody there. Okay, Boris Tomasik, go ahead.
Yes, hello. I was wondering about this region of validity, which is also in this conclusion page. So how do you determine this mu b over t smaller than 2? Like why is it 2 and not more or less?
Yes, so the idea is that, for example, when you do a Taylor series, you check the order up to which you can go, and then, let's say order 4, and then you compare to order 6, and you see whether you see a big deviation or not. And what we could see is that if you go to the next order, in this range of mu b over t smaller than 2, the two orders agree with each other, and therefore we see a convergence within this region that we trust is there. Whereas outside this region, you see big deviation between the order that you stop at and the next one, and therefore because of that, you conclude that here you would need to go to a higher order to see the same level of convergence.
Thanks.
You're welcome.
Okay, other questions? Okay, don't see anything right away. So actually, I had a question of my own. Let me see. Somewhere around page 20, you were showing the dependence of this Taylor coefficients, I believe P2, P4, yeah, as a function of temperature. And something that was strange here to my eye was actually non-monotonic dependence on the temperature. Doesn't that imply that there is something going very wrong with the expansion when that happens?
No, I mean, so the idea is that, so if you think about it, it turns out that, so these coefficients, if you notice, they are only even powers of the chemical potential, because the odd powers are all 0 because of charge conjugation symmetry. So basically, taking a second derivative with respect to chemical potential, which is basically if you think about it, chi4 is the second derivative of chi2 with respect to mu b, and chi6 is the second derivative of chi4 with respect to mu b, corresponds to taking one derivative roughly from the point of view of the shape of the curve with respect to temperature. So the idea is that the shape of these coefficients basically is not unexpected, because if you look at chi2, the second order coefficient, you see a rapid rise. And then if you would take one derivative with respect to t of this quantity, you would see a peak, more or less where chi4 shows a peak. So there was, in the literature, this was demonstrated that there is this equivalence between second order derivative with respect to mu b and first order derivative with respect to t. And then, of course, if you look now at chi4, you see that here you have a rapid rise. So you would expect here a peak that you kind of see here in the data, at least if you compare with the HRG model, you see kind of a peak. And then where you have a peak in chi4, you expect your chi6 to go to 0. And then here where you have a decrease, you have another inflection point which corresponds here to this dip, and then you have the asymptotic behavior. So this behavior of higher order coefficients, not the quantitative value, but the general shape of the curve, you can already infer from, for example, the same is true here. If you look at chi6 and then chi8, because chi6 has two peaks, you expect chi8 to have two zeros, and in fact here they are, and then more peaks which corresponds to the inflection point in the other region. So this behavior is well understood.
I see. Okay, I see two other raised hands. Michael again. Michael, go ahead. I think you were first.
Hi, Claudia. So when you guys were looking at the width of the phase transition, you were primarily looking at like the chiral susceptibility width, right?
Yes.
And if you do look at the trace anomaly as well, is it similar in that the width of the bump in the trace anomaly does not change as a function of mu b?
We didn't directly look into that. That's a good point. So the bump on the trace anomaly sits, however, at a temperature which is higher than the transition temperature, right? It's right in the above in the QGP phase. But it is true that, in a sense, the width of the width of the trace anomaly is something that we haven't explored. So I should really look into that to have an answer. I don't know the answer because we haven't looked at that. But that's a good point. So it would be interesting to see whether that one also shows a constant behavior as a function of the chemical potential. The question is, however, whether you would be able to directly relate the trace anomaly width to a signature of a first order phase transition. So I should look also, I don't know on top of my head if that quantity is also expected to diverge at the critical point or not. Yeah. So that's something that also has to be.
Yeah, we can with HTLPT, we can try to adjust at least coming from above if, you know, the region in which the trace anomaly or the chiral susceptibility starts to get a peak. It won't turn over because we don't have the hadron phase, but we can at least look at the region coming near TC, whether it, you know, it shifts a lot, if it gets wider or narrower.
Okay.
And with the trace anomaly, it doesn't seem to.
Okay.
We're calculating the chiral susceptibility now, so we'll see.
So the trace anomaly you looked as a function of mu b also? And it is constant as well?
I'm just looking at a plot right now. The width doesn't seem to be by eye very much different, but.
Okay, interesting. Yeah, we will look into that. We just never did. So thanks for the tip. Okay.
Okay, I did see another hand. Kirill, are you still having a question? Or
yes, sorry, I just
go ahead.
Delete this raising hand thing. So hello, thank you for the talk a lot. I have a question about the finite width of the chemical freezer. Sorry, of the phase transition and of the crossover, sorry, and how it connects to the chemical freeze-out. So you showed that there are actually two different chemical freeze-out lines, which are both well within the width of the crossover. So does it mean that it's enough to model? I mean, since it's a crossover, not a real phase transition, is it enough just to neglect this effect of having those two different freeze-out lines for S and for UD? Or does it have some physical, some important consequences for modeling?
Well, that's a very good question. And the idea is that it depends. So the physical picture that we have in mind by looking at a picture like this is that, okay, you have a let's say we start from low temperature and going up to high temperatures, right? So at low temperature, you have hadrons, and then these hadrons, the ones which contain light quarks, start to liberate their degrees of freedom at lower temperature, because the light quarks are the lightest degrees of freedom. And then as you increase the temperature, finally also strangeness gets liberated. And then when you are up here, you have only quarks and gluons. So it's a very intuitive picture that we can imagine. But the physical consequences of that, it depends, I guess, on the observables that you are looking at. So I know that people have been trying, for example, to model these two freeze-out scenario in hydrodynamic simulations. And I think the two freeze-out scenario worked better in some comparison with data, but out of top of my head, I don't remember. But it depends on what you are looking at. So for example, one important consequence that this could have is in the early universe. Let's say you come from above, and you, in the early universe, when you had a hot quark-gluon plasma universe, and then you get at first confinement of strangeness, and then confinement of light quarks. So it could be that these clusters of strange matter formed early in the universe and ended up populating, leaving the fireball and maybe populating the core of compact stellar objects, or something like that. So that would be something that is interesting in this scenario, the consequences of having strange quarks hadronizing and freezing out earlier than light quarks coming from high temperature. I could see some astrophysical interesting application for that.
Okay, thank you. So basically, those two different lines being within this crossover makes actually sense in the sense as you. So this is what one should understand, right? That that the crossover is exactly something like having hadronizing different degrees of freedom subsequently.
Yeah. Yes,
okay.
well, yes, because it's a very broad transition, right, from a hadron phase to a pure quark phase. In between, it's a broad range of temperatures where things change slowly. And our interpretation, at least from this picture, is that probably this slow liberation of degrees of freedom is driven by the mass of the quarks, which is the lighter ones are liberated first, and then as you go to heavier masses, they get liberated a little bit later. We are talking about very small difference of about 10 to 15 MeV, so it's not a dramatic effect, but it is still something that the data seem to reflect.
Okay, thank you very much.
Actually, I kind of have additional comment regarding that. I was having almost a question about this, but now it's half answered. The thing is that such a dramatic change here, it's like nearly 15 degrees MeV temperature difference, that the freeze-out temperature seem to be so different. It's related to the rate of interactions, inelastic interactions primarily. And as far as I know, we calculated with Kapusta this long time ago, the temperature dependence of that rate is very strong, while the expansion rate remains more or less the same. So actually, even though the temperature might be only 15 MeV difference, the effects could be dramatic, especially in heavy ion collisions where the expansion rate is large, unlike the universe where the expansion is very slow in a way. So in fact, that kind of brings the actual question: how could you define the cross correlations between baryonic, let's say, and strangeness charges, since this decoupling of results could be so different?
Yes, so basically the cross correlator, it all depends on the particles which make up this cross correlator. For example, for baryon strangeness correlator, it turns out that the proxy which works the best to describe the full curve basically contains lambdas and kaons, which we already know from analysis of fluctuations of lambdas and kaons by themselves as particles. They freeze out at a higher temperature. So it is not a surprise that the ratio of quantities which contain only lambdas and kaons is also favoring a larger temperature. So if it would be, you know, also protons included in this correlator and playing a big role, then probably things would be not so trivial. But it turns out that the contribution, for example, of the proton to kaon correlator, which is what star collaboration was actually looking at first as a proxy for this baryon strangeness correlator, it turns out to be extremely small, almost consistent with zero. So this baryon strangeness correlator is really mainly driven by strange baryons, and so that's why it is not surprising that it follows the strangeness behavior. Whereas for the for example, baryon electric charge correlator, in that one you would have the main contribution coming from protons, and therefore that one would probably I think we have it in the paper, I don't remember on top of my head, but it probably would follow the lighter freeze-out curve. So it's still, even though you are looking at a correlator between different conserved charges, the main contribution to that can still very well be separated in terms of particles, and those are the ones that in the end drive the temperature, and those are the ones that can be that star measures.
Okay, I see. So essentially, you're not trying to consider all the particles, because then it would be sort of meaningless on the one hand, but also it's not like all of them contributing equally.
Yes.
And then it would make sense, I guess. Okay. Any other questions? Any other questions from the audience before we will stop wrapping this up? I don't see immediately anything here. So if there is nothing else, I would like to thank Claudia for a very nice presentation.
Thanks a lot.
And very detailed with all the information. So thank you. Thank you for all the time you spent.
Thanks for inviting me.